I'm going to split the talk into 3 parts. The first one will be on disjunctions. The second part will be somewhat unrelated on lenses. And the third part will combine those two. I don't know if that sounds interesting. If at any point I say something which doesn't make sense, shout out, and I'll try to make it clearer. I can't promise anything. But let's jump into disjunctions. You OK? And maybe unique for any conference, we're going to open with a lesson in variance. Is everyone excited about learning about variance? I can hear the groans. OK, so I'm going to define some case classes. These are just types. One's called covariant, and appropriately it has a single type parameter which is covariant. That's what the plus is. Likewise, there is an invariant one, which has an invariant type parameter, and there is a contravariant one, which is, of course, contravariant, thanks to the minus sign before the t. So I'm going to do a few examples, well, one example with each of these, just to give you a background to variance and how it works in Scala. Could I just have a show of hands? How many people understand variance in Scala? I'm impressed. OK. How many don't understand variance? OK. I'm going to tell you about it anyway. So in Scala, if we construct a list, and we put 2 values in that list, and they are different types, so one is an int, one is a string, the compiler has to come up, it has to type check this expression. It has to come up with a suitable type for this list, which means it has to come up with a suitable type for the elements in this list. And what it does is it calculates something called the least upper bound. It finds the best type it can that is suitable for all of the elements of the list. And when you have an int and a string, it turns out the best it can do, the absolute best type which satisfies, which is suitable for all of these parameters, is any. Ints and strings have very little in common. So we go right to the top. And this is what happens with covariance. And indeed, if we were to wrap those parameters, in fact, we don't even need the values. We can just specify int and string on our covariant type. If we constructed this, you would notice that it infers the same type, but wrapped in this covariant wrapper. This type is just a wrapper around these other types. The behavior of the least upper bound operation is the same regardless of whether it's wrapped or not. So we get covariant of any. Now, the flip side is when we have a contravariant type. Put the same values in, but this time wrapped in contravariant. Sorry, same types in, wrapped in contravariant, int and string. Does anyone know what result what type will be inferred here? So nothing. So nothing is like the opposite of any. So if any is the top type, nothing is the bottom type. Wrong, but what you gave me is a lower bound, but it's not a greatest lower bound. What will be computed is the greatest lower bound, and the best type the compiler can come up with, which satisfies all of these parameters, is contravariant of int with string. Is anyone surprised by this? Yeah, a few people surprised. OK. It's just what happens. That's what happens when you calculate a least upper bound, a lub, over a contravariant parameter. It flips the lub into a glub, a greatest lower bound. And it turns out that the greatest lower bound for types like int and string is int with string. It's the intersection type. And I will briefly look at invariance. If we use the invariant version, then the type that gets inferred is even more complex. It is an existential that is bounded by that greatest lower bound. But I'm not going to spend any time looking at this. This is here for completeness and for you to ponder about later. Now, I said this is about disjunctions. A fundamental part of me providing disjunctions in Scala is type-level sets. So in the same way that we can construct a set, which is a set which is the value of other values, a set of values represented by a value, we want to construct a type which represents a set of types. And my idea of how to do this is to use intersection types. So you're maybe familiar with, well, I'm sure you're familiar with intersection types. One example is product with serializable, which often occurs when you don't want it. Something of type product with serializable is a product, and it is a serializable. It's both of these things. It's the intersection of these two sets or types. And in Scala, for any two types, A with B or B with A, we have equality under reordering of those elements. These are the same type. Does anyone want to disagree with that? Tomo?
I wouldn't say disagree, but the mechanics of that are a little weird considering that there's a definite meaning to order when you actually declare.
Right, so Tomo is aware of certain problems around this. The problems occur when you do a type projection on this type. So if you had A with B hash C and B with A hash C, these could potentially produce different types if they had a type member and if we were looking at that type member. We're going to be careful not to do anything like that, because that is an unsoundness hole in Scala, so we just avoid it completely. We will only ever construct these types as intersections. We won't do anything beyond the intersection, like projections. And within the compiler, anywhere that the compiler expects an A with B, you can happily provide it a B with A, and it compiles fine. So that is one thing we get. We also get deduplication. A with B with A, the compiler considers to be the same type as A with B. It sees that A is repeated, it removes one. So you may be thinking this looks a little bit like the semantics of a set. We have uniqueness and we have unorderedness. But for the set to be useful, we need something a little bit more than that. It's all very well being able to construct sets, but if we can't do anything with them, then it's a little bit useless. So I think the most important operation in set theory, and if I sort of vaguely say that subset and element of are kind of the same thing, to find out whether an element or a subset is within another set is probably the most useful thing you can do with a set, of whatever set that happens to be. And it turns out that if we use intersection types for our encoding, the set of types A, B, C contains B, or the expression A, B, C contains B, is equivalent to A with B with C is a subtype of B. So set contains is equivalent to supertype. Can you see how that works, or how that is true? Can anyone not see how that's true? Is everybody seriously confused? I'm going to tell you it's true. And it's kind of obvious. A with B with C is the type of all things which are A's, which are B's, and which are also C's. Therefore, B is a supertype of that. Check. And the expression on the left is obviously true from the definition. And we observe that subtyping is absolutely fundamental to the Scala type system. It's the most important operation it does. Pretty much every single expression when the compiler is type checking involves doing subtyping checks. So what we've done here is we've created an equivalence between what I think is the most important operation in set theory and the most fundamental operation in type checking in Scala. So this, I hope, should give us confidence that this is a useful representation of type level sets. For a more concrete example, say we have the set string int and double. That contains int. Good. OK? I'm saying that is equivalent to string with int with double is a subtype of int. Now, is anybody a little bit confused by the idea of string with int with double? I mean, it sounds weird. How can you have something which is a string and is also an int and is also a double. No such thing exists. You can't construct one of these. But the type system in Scala can still talk about it. It's still a useful type. It's distinct from the nothing type, which also has no elements. They're distinct because type theory is not set theory. But we're able to talk about it, we're able to make use of it, we're able to use it for things like deriving implicits. We're able to use it for a bound on other types. So it is a useful type for the compiler to work with. Now, in my library, Totalitarian, which I'm introducing today, the first of two libraries I'm introducing today, we're going to provide a type which is called Disjunct, which is basically the same as a sum type or a disjunction or a coproduct. The thing in brackets is effectively the categorical dual of this thing. So sum is the categorical dual of product, disjunction, conjunction. I don't even know if cosum exists, but we've already got product above. So you can consider the idea of a cosum. Unions and intersections. So in Dotty, disjunction types will be called unions. This is something Dotty has and Scala doesn't. And you're probably familiar in Scala with a very special case of this sort of construct, which is either. Either is one of two possibilities. And the sort of product equivalent of that is tuple 2. It is two things kind of bundled together in the same object. So what Disjunct does is it provides a wrapper for instances of one type chosen from a set of several. And I say it's an arbitrary set. So you're probably familiar with sealed traits. Everyone okay with sealed traits? Yeah, I can see. Put hands up and go, like, cheer for sealed traits. Okay. That's the first cheer they've ever had in the history of Scala, I think. But yeah, I was getting these little nods tonight. Be enthusiastic. So sealed traits, at the time you define the types, you put them in a coproduct. That's what that sealed trait represents. But you can't create ad hoc sealed traits later. You can't create ad hoc coproducts. A disjunct you can, and that is what that is what Totalitarian provides. And the encoding uses this trick of type-level sets. It uses intersection types to represent union types. Now, I've mentioned things like categorical dual with respect to coproduct types and product types, and intersections and unions. There are other duals that exist in Scala. So the least upper bound is the dual of the greatest lower bound. The contravariance is the dual of covariance. And it turns out you can flip these things, and we can still make sense of it. So essentially what we're going to do is take advantage of this fact, and by using union types in a contravariant way, as opposed to, sorry, by using intersection types in a contravariant way, we can use the behavior that Scala provides for intersection types in a covariant way. We essentially flip the arrows, we flip the bounds, our least upper bounds become greatest lower bounds, and waving my hands a bit, it all just works. It's a bit harder than that, but I will talk you through it. Maybe. We'll find out before the end. So in Dotty, you would write a union type as int, pipe, string, pipe, double, or int or string or double. That's what it is. You have a thing which is an instance of that type. It's either an int, or it's a string, or it's a double. In Totalitarian, the type is going to be represented as disjunct of tilde int with tilde string with tilde double. And I've just introduced this tilde thing without an explanation. So let's explain why that is there. What is that magic wrapper type? We have a problem, unfortunately, in that Scala has subtyping. So if you have the type exception with string with throwable, there is a subtyping relationship between two of those types in that intersection. That simplifies, unfortunately, to exception with string. But exception already implies throwable, because exception extends from throwable. So the compiler will deduplicate those throwables. There's one that's already provided through the exception, and then there's this one here, which just gets deleted, effectively. We don't want to lose an element. We don't want to have a type-level representation of a set and then randomly lose elements from that intersection. So what we do is we wrap it in any invariant wrapper, and I've just invented this type called tilde. Its type parameter is invariant, and by wrapping every element in the intersection in that tilde type, we lose the subtyping relationship between those two. If it was a covariant type, we would keep the subtyping relation. If it was contravariant, we'd get the reverse of the subtyping relation. But invariance allows us to lose that, and it makes, so whilst exception and throwable are related types, tilde of exception and tilde of throwable are completely unrelated types. They're as different to the compiler as int and string. And this is what we want. It means nothing will be lost from the intersection. So that's just a bit, in some sense, it's a bit of a hack to make it work. In another sense, I reached for the obvious feature of the type system to solve the problem. It turns out there's only one thing that does. So let's create some of these things. Here's a disjunction of the value 1. By the way, I'm going to stop saying tilde before every type. This is a disjunct of int. It's not really a disjunct at all, because there's only one type in the intersection. Likewise, if we had a disjunct of 2, there's only one type in the intersection. It's string here. We could put these together in a list. And what happens when you put things in a list? The compiler tries to find a type that is suitable for all of the values, all of the elements of the list. So we've got 3 elements here. The last one's obviously disjunct of double. What's the return type? Well, it's kind of what we wanted. This gets inferred. The compiler infers the type disjunct of double with string with int. We have a type level set representing all of the types that might be represented by the elements in this list. And the types of the elements have now been widened. We've lost the fact that the first one was an int, the second one was a string, the third one was a double. We've found a unified type that represents all of them. But that type is precise enough to represent the fact that the values we're working with could be one of these, any one of these things. So if we've got a value which is a disjunct, what can we do with it? There's the value we're going to work with. It's a map, so let's map over, sorry, it's a list, so let's map over that list. So for each element in that list, we're going to use some syntax which is provided by Totalitarian. It's normal code, there's no macros, there's no magic going on here. And I will define what happens for each case. So when it's an int, let's multiply that integer by 10. Okay? It's a reasonable thing to do. When it's a string, we will add an exclamation mark to the end of that. That is a normal method call. When takes variable length arguments. So we can have any number of these matches on here. But we do a different thing depending on the type. There's a question somewhere.
Yeah, is this exhaustive? By which I mean, do you get like...
Yeah, hold on for the next slide. Spoilt the surprise now. So the result we get back is once again a disjunct of string with int. Because we don't change the type in any of these lambdas, but we get the integer multiplied by 10 to now has an exclamation mark at the end. So that is, I think, what we would hope for, if not what we would expect. Exhaustivity checking, who would have thought? So we've got three elements in this, or three possible types in this list of disjunctions here. double with string with int. And let's say we apply that when method again. When it's an int, we multiply by 10. When it's a string, we add an exclamation mark. And we don't specify what happens with a double. What happens? Any guesses?
Either exception or identity function.
OK. But yeah, so Luca is right. So what we would like is a compiler error. And the library is called Totalitarian for a reason. It works with total functions. This is a partial function. It doesn't specify what happens in the case where it's operating on a double. The compiler says not all disjunction cases have been specified. And it does this at compile time. It doesn't tell you at runtime when you can't do anything about it. It stops you ever compiling this code and putting it into production. So what it does is it does a bounds check. And it looks at the types you've provided here. It infers a type based on the types you're matching on, int and string. And it compares that to the type of the disjunct. So it says, it tries to find evidence in the compiler using this implicit type here, less than equal to less than, which means subtype. It says, is int with string a subtype of int with string with double? The answer, you have to think about it quite hard because we're dealing with, remember, subset of is sort of backwards from, subtype of is sort of backwards from subset. Subtype means superset. Subset means supertype. So is this a subtype of this? No, it's not. We can't find the evidence, therefore refuse to compile. And of course, if you provided on double there, this type here would be equal to this one. Equal is a perfectly good subtype, so that's fine. If we provided half a dozen different matches on here with different types, that would also be fine. We wouldn't use them, but it would be they would be suitable for making this function total. So that all comes for free with the type system. Now, there's one other fancy trick you can do with disjuncts in Totalitarian. And I want to emphasize this does not use macros. You'll look at this and you'll think, how on earth do I do this without macros? But I will try to explain on the next slide. So we create our disjunction, our list of disjunctions. And we're going to map over it. And this time, if I get an integer, I'm going to just use the identity mapping. So leave it the same. Don't change that 1 to anything other than a 1. But if I get a string, I want to get the length. Now that is also an integer. So what is the return type of this expression? Any guesses? Thomas?
List of disjunct of ints.
It's a reasonable guess. Reasonable guess.
Elide the disjunct one.
Well, you say just elide the I do a very clever type level trick to make this work. But this is what you get without macros. The compiler or the type system is able to work out that those return types are all the same. And it just unwraps the value. It's safe to do so. And this is something you will commonly do if you're working with disjunctions. When you have an application, you have inputs going into that application. You often need to branch on those inputs. Depending on what the inputs are, different code paths will be run. But essentially, you want to sort of move towards a unified result. The more you're sort of passing branches around your code, the more work you've got to do, the more code you have to write to handle them. So the sooner we can combine these things and work with them as a single unified type, the better. How do I do that? OK, I'm going to, by the way, this is the most complicated slide in the deck. I'm going to try to explain it, but I'm also aware that what I'm going to give is a very vague overview of how it works. So don't panic if this doesn't make sense. I expect it to not make sense to probably 90% of people here, and at least part of that will be because I will give Not a fantastic explanation, but I'm going to try. Let's see how I do. So when we're typing that when expression, normally if we have a type parameter that appears in the var args, in each of those clauses, we would infer one type that corresponds to those. But instead of inferring one type, we're going to infer two different types. Why would I ever want to infer two different types? Well, I'm going to infer one covariantly and one contravariantly. So remember what I said at the beginning. One will effectively be the lub of those types, the least upper bound. The other one will be the greatest lower bound of those types. So they will produce different values, different types, should I say, potentially. And then the value I return, the thing that in the last example was a list of int, or rather it was just an int, in fact, for that disjunction. That is going to be dependently typed. It's going to be dependently typed on an implicit. And I'm going to search in implicit scope for an instance of this implicit which is determined by the two type parameters, one from the greatest lower bound, one from the least upper bound. And I'm going to provide two implementations of that implicit with different priorities. One is going to be higher priority than the other. The one with the higher priority will match only when those two type parameters are the same type. And there will be a method on that implicit which will unwrap the disjunct. It will get the value out of the disjunct if and only if those type parameters are the same. If that implicit doesn't match, the compiler goes and finds another implicit. So there's a lower priority one which will match anything. It will never fail. It will never fail to match. But given that the first one hasn't matched, it implies that those two type parameters are different. And that one will return the disjunct unchanged, so it will still be wrapped up. That's it. Why does it work? Well, the punchline is that the greatest lower bound and the least upper bound will be the same type, only in the cases where all of the return types are the same type. By virtue of that, we can take advantage of the machinery of implicits. We can take advantage of dependent method types to return a different value. And the return value can be dependent very much on whether all of our clauses in that when block are returning the same type or returning different types. And that is how we do it. Yeah?
Does that operate on the real inner type string and int or on the tilde wrap?
So the question was, does it operate on the inner types or the ones that are wrapped in the invariant tilde type?
Basically, if I have exception and throwable,
Yes.
I will have to map if I will have throwable. A list of throwable, or if I have a list of disjunction, exception, throwable.
So I could have implemented it either way, and the question is, do I want to keep distinguishing between exception and throwable? I chose to implement it where they are distinct types. You could always work around that by providing explicit type annotation on the exception to make it throwable. If you had one case that was dealing with exceptions, one case that was dealing with throwables, you would upcast the exception to throwable, and then you'd get the unification. And that's a worthwhile question to ask, because there are alternative answers, and maybe what Renato has described would be more useful. I don't know yet. Nobody's really using this. So it's very much open to debate. Another follow-up question, go on.
Well, it's not a question,
Okay.
it's more comments. I find it strange that depending on what I have when I map, I get no rapid type or a disjunction. I think it's strange. It operates different depending on what I have. I would expect
Yeah.
to always have a disjunction.
Yeah, but I think that's familiarity with non-dependently typed methods. So from the point of view of a language like Idris, which is entirely dependently typed, it might seem, the opposite might seem strange, that it couldn't disambiguate. Scala has all these features. They're sometimes harder to access than they are in a language like Idris, but it does provide them. And I think there are some exciting ideas to explore that do that. Yeah, it can be surprising. Indeed, a lot of things relating to implicits can be surprising. This is the way it's done. This is interesting research rather than definitely the right answer. So I'm done with disjunctions. Go on then.
Just a quick question. So you very explicitly said that the reason it's totalitarian is because it's based on total functions.
Correct.
Have you explored or maybe even found ways of implementing something like partial mapping without unfortunate white box macros?
Without white...
Basically, it's something along the lines of, I want to take only the ints in my list of disjuncts. And,
right. So yeah, you could... there's a method on disjunct which will say get int. That returns an option. I mean, it's still total because it can return none. But it says if it's an int, return the int. Okay. And I don't know what else will go into the API of disjunct. It doesn't have very much at the moment, but there's scope for new ideas. So something completely different, if everybody's ready to move on. Yeah? Had enough of disjunctions? Let's look at lenses. How many people here have already used lenses on algebraic data types like this? So a few people a little hesitantly putting their hands up. Does anybody not know what lenses are? Because I'm going to tell you anyway. I'm going to tell you why they're useful. What I'm not going to tell you is the benefits of using immutable rather than mutable data types. So I'm going to presume that we're all subscribed to the idea that immutable data is beneficial. And let's say we have a set of case classes like these: registration account, company, payment, and they're related. You can construct an instance of registration which is composed of the other case classes and some strings and booleans and so on. So I'm going to use this for most of the examples in part 2 of this talk. Now we can observe that accessing values inside an instance of, for example, registration is actually very easy with case classes. We call .account, .payments. Payments is a list of payments, and we map over that to get the Boolean confirmed. And the return type, shouldn't be surprising, is list of Boolean. Nobody's surprised by that, I hope. So that's pretty easy. It's a one-liner, nothing complicated. But the problem is when we want to update that. If we wanted to change those values. Now, when I say change, I actually mean creating a new registration instance with different values. So let's say we wanted to confirm all of the payments in our registration. The first step would be to construct a new list of new payments. So for each payment, we will copy it, changing the confirmed value to true. This will give us a list of new payments based on the old one, which comes from reg.account.payments. But we haven't got a new registration yet. We've just got a new list of payments. And we can't even yet get a new registration. We need to, first of all, make a new account. So we get a new account, update the payments value to that new list we've just created on the previous line. And then to get a new registration, finally, we replace the account with the new one. So in order to change one element at the leaf of this algebraic data type, we have to change references every step of the way. We have to construct new objects all the way up the stack. It's three lines of code, or you can even write it like this. You can inline everything. So it's a single expression now. This is the point-free style. But it's a lot of code just to make what seems like should be quite a simple change. And this is where lenses help. Lenses give us getters and setters which focus on certain elements in an algebraic data type. And they use the analogy of light passing through lenses, through optics, to focus on elements. And when focusing on those elements, they can change the elements or just return them. So I'm going to show you my second library of the day, optometry. This is something I had a recent flight to San Francisco, which was 11 hours long. And I didn't have any internet, so I thought, what can I do for 11 hours? And I wrote a lens library. And it's called optometry. And it does actually use, I know I'm reluctant to use macros unless I really need them. This does use macros, but it allows us to construct a lens like this. So if we wanted to get the account from a registration, here is the base type we're working from. And the syntax is to do _.account. That will give us the account back. That's very similar to what you'd have in Monocle, if you've used Monocle. Likewise, given an account, we can get the payments from that. Remember, that's a list of payments. And then we can compose these two types together, which gives us a lens from registration all the way to the list of payments. In order to apply that lens, we take the lens we've just produced, get reg payments, and we pass it our hypothetical instance of registration. And what that will return is a list of payments. Shouldn't be too surprising. It just accesses the value in that registration. And if we wanted to change that value, we would use syntax like this. This is using the update syntax that Scala has. Who is familiar with update? So if you name a method update, and you give it 2 parameters, you can apply it in this style here. And this will desugar at compile time to get reg payments, reg, comma, and then the thing on the right-hand side of the equals. But in syntax, we can use this desugared, this sugared version, where it looks like we're just setting a value. This actually doesn't mutate anything, but it returns a value, which is a new registration, with the payments replaced by this list here. So there's nothing particularly impressive on this slide. This is stuff that's all been done before many times. But optometry gives you some more advanced things you can do whilst keeping very lightweight syntax. So here's a more complex example. Again, we're starting from a registration, and we can combine more than one dereference in the same lens. So we're going to get the account, we're going to go straight to the payments. Now, payments is a list of type list of payment. We can't call .confirmed on that because that only works on a payment, not a list of payments. We somehow need to get across the list to access the elements inside. And there's also the problem that there's many payments potentially in that list. So how do we make sense of this? Well, we can stick I'm going to call it for now a thing. We can apply a thing to payments, which allows us to get across it and access the elements inside of type payment. And then we can have a method name here which operates on those payments. So this, I hope, is intuitive, at least. The result we get from this is of type list of Boolean. So the Boolean comes from this confirmed value, but it has to be a list. It can't just be a single Boolean. The list of payments, or the list that comes from the payments, sort of collapses down upon this value here, and we have a lens which isn't focusing at just a single value, it's pointing at many. So we get a list of Booleans. It gets interesting when we try to use it as a setter. So we're going to confirm all of these payments, and we can do it in one go. We don't have to map anywhere. The lens does the mapping. The lens is focusing a beam which splits across every element in that list, and it sets all of them to true in one go. The result, as always, is a registration, because it also updates, it also generates the code that produces those copy calls that updates the references all the way up the stack. So this is, I think, this is very nice syntax for updating many things in an immutable data structure all at once. Does that look good? Silence. Could you just repeat, if the class has something of payments?
Well, for example, I have a balance number in account, which has to be updated as payments confirmed. How to do that?
So you would need to update that in 2 steps, I think. There might be a way to do it. With the tools I will show you over the next few slides, there might be a way to do it, but I think generally the best thing would be to update the payments and then update the balance. But in that case, I might try to argue that you have the state you are storing in an ADT like that is duplicating information. It has the risk of being in an inconsistent state. So it's an inconsistent state if you have payments which don't add up to the balance. So the balance is kind of a cache in a way. It's a cache for the sum of the payments. So it's useful, but it's over-representing the state you need to represent that data. But having said that, yes, maybe the solution would be to do 2 different lenses and update them separately. So I talked about this thing called each. I didn't really explain what it was. I'm going to call it an optic, because I don't really know what it is. And this is the definition of an optic. It has a map method and a set method. And I'm not even convinced this is the right implementation. This happens to work. It works for all the examples I've tried so far. But the signatures are a little bit complicated. We have 2 type constructors provided here. It seems to work, but I demonstrated this, so I showed this to a couple of friends of mine, and they spent a lot of time looking at this, and they didn't know what it was either, which leads me to believe it's, well, there's kind of a gray area between something that works and something that Runar and Jon believe should be a part of a functional programming library, and that gap has not yet been closed. So maybe I will end up refining this API later. For now, it does work. And I'll show you an implementation for the each optic. The implementations are actually very trivial. Our map method is implemented by map. We're mapping over a list the function that's provided here. This is used mainly for getting. When we get a value out, we're mapping a function. So in the case where we were getting the confirmed values from our payments, the function that would get applied here is accessing the confirmed values. The list that we start with is the list of payments that we get from the lens up to that point. So the result we get back is a list of B, which for confirmed would be a Boolean. So in that particular example, you can see what's happening there. The set value is what happens when we are setting. And it takes 2 parameters. There's f, which is the original list, corresponds to the f type there, and g, which is the updated list when we've done some update, when we've done some modification on that. And that returns just the new list. It actually doesn't include the f, the original list. And in fact, if you were to update the values update all the values in a list, we don't need the original list to work out how to replace them. We just need the new one. We discard the original one that had those, in our example, the old payments in. That will make more sense when I show you a different example, head option. So when you call head option on a list, it will give you an option of the head if the list has one or more elements, or it will give you none if it is empty. The implementation of map looks much the same, except we're first getting the head option and then mapping across that. So we're sort of discarding the tail of the list. You'll notice that we now have two different types here, not list and list, it's list and option, because head option returns an option. So we need to have both of these types. One is the source, one is the type we're going to. And then the setter is now slightly more interesting. It's not just returning G, because we don't want an option returned. We need, if we update the head element on a list, we still need to get a list back. We can't return an option. An option would be badly typed. So we look at the original list, F. If it was empty to begin with, then there's no head to be changing, so we leave that as empty. If it had at least one element, then we take that first element, we actually get rid of the first element, H. The head is no longer used. And we attach the tail to the result, G, the option. We have to convert it to a list first. So we're simply replacing the head of the list in this particular case. So the optic interface gives you the ability to write definitions like this. And head option would be used in this way. So say we want to just change the first payment in a list. Maybe we have a convention in our data type that you modify only the heads. The most recent payment is at the head of the list. We want to look at the most recent ones. So we apply our lens to a registration. We now get an option of payment, not a list of payment. There's only at most one. And if we wanted to replace that with a new one, we simply use this syntax, give it the new payment. We're going to delete the head payment if there ever was one, substitute this new one in, and we've updated that so there is now a registration returned. So this is quite conveniently pointing at the head of the list. You could also imagine an optic which, say, gets an element at a particular index, if that index exists. You could write index, and then you could parameterize it. You could say, get the third element if you wanted to. Or yeah, I've got an example of that, of a predicate, in fact. It's probably a couple of slides away, but you'll see that. So this was our structure. I'm going to look at a different part of the algebraic data type now, a more complex example. Company is an optional field. And in the same way that you can't sort of get past a list when you're accessing elements in your ADT with a lens, we have to get past the option. So option is a little bit like each, except it works in options rather than list. The company has an address. The address is a list of strings representing the lines in that address. And we want to point our lens at each element in the list. So we apply the lens. Any guesses as to what the return type will be for this? List of addresses and a type. Address is list of string.
Option of list of string?
Yeah, option of list of string. What happens is kind of the only thing that makes any sense. I'm confident that the library does the right thing because the types all line up and I don't have to cast anything. That gives me confidence that it's a sensible implementation. And the return type we get is the string that comes from each element of the address, the list that comes from applying this each, and the option that comes from the company. They sort of collapse down to this result. And you can chain any number of these together if you want to. Renato, yeah.
Maybe I missed it at some point in your explanation, but in that case here, you're passing an company and to address. So what is the type of company? The type of address? Is that a lens?
So yeah, it's a good question. It's a good question which is sort of the wrong question because this is simply a definition of the lens. It is actually, the way this is implemented is actually with dynamic the dynamic trait. And the macro goes and checks that the dynamic applications exist, are valid. The type inside the brackets is always optic, but the types of these things here, the dereferences, these are dynamic, and the macro manually does checking on these to make sure they make sense.
Okay, so using dynamic type, how do you call it?
Dynamic trait, dynamic type.
You just kind of add a kind of dynamic methods that.
Right. So the dynamic.
If I don't have a company there.
Yeah, I'd like to treat this as just the syntax for describing lenses, but just to give you a very, very brief explanation as to how it works. This is a type from dynamic to dynamic. You can keep calling methods with any name you like on it, because that's what dynamic allows. But then the macro will go and check that it's correct afterwards.
Does that mean that the parameter in the lens definition is not registration? It's just some arbitrary dynamic type?
So the macro will use this registration type. This is a concrete type. The compiler will, or the macro will look at this type. It will check. It'll know that the underscore is effectively typed as registration. It will look at the type, the signature of registration. It will check that it has an account field. If it does, fine. And then it'll do the same thing with company, but it now knows that the return type of that address field is, that account field is account. It's checking against account now.
Okay, I think I got this question. I think the question was the underscore, not registration.
The underscore you should view as a registration, in the sense that the macro will constrain the methods you can call on it to only those that are available on registration.
The implication, one implication, for instance, is that you don't get things like auto-completion and IDE.
Correct. You would not get auto-completion. Yeah. You get as much auto-completion as you ever do with Vim, which is my development experience. But so anyway, the return type we get from this is option of list of string, and it comes from collapsing the functor types in option and each around the final type of the value you're accessing. We can actually, as well as just getting and setting, lenses can also modify. So they can take the existing value in a particular position and change it in some way. And there's a modify method for doing that. We can modify an existing registration using the lens, pointing at every line in the address. And let's say we wanted to add a comma to the end. I mean, I know it doesn't really make sense to have a comma on the final line, but you could even change each to init so that it works on only the first, or all but the last element of the address. But we can do that modification, and of course, as always, we'll get back a registration. So I think that's quite nice. There are more things you can do. You can have more flexibility with these optics. But what I want to do now is the obvious thing, which is to combine. Oh, hold on. No, we've got one more slide before we go on to the next step. Oh, something quite funny has happened. I've got speaker notes, which are meant to show me the next slide, and it's showing me 2 slides ahead now. This is quite funny. So I'm going to have to try and make sense of this. So Thomas, I think, said you could potentially parameterize those. You could parameterize those. Oh, it's completely broken now. Parameterize those optics. So we could, for example, create a filter optic, which gets all of the payments. We can apply one optic directly after another one, gets all of the payments which are not yet confirmed. So this returns a filtered list of elements. We apply that to our registration object. So although we're filtering on a Boolean value, which comes from the payments in that list, the value we get back is an amount, which is of type money. So this is quite useful. And we could even modify it. We could modify the ones that are not confirmed, and we could set the amount to 0 if that's a useful thing to do. We get a registration back, as always. So next step is to combine these two ideas, obviously. What happens if we changed our algebraic data types to include a coproduct, a sealed trait? So let's say payment has two different parts now. It's either a refund or it's a card payment. And the information they contain is kind of similar, but for refunds, we have a flag which is whether it's processed or not. For card payment, we have a flag which determines whether it's confirmed. There could be all sorts of different things you could do here, but for simplicity, I'm keeping them similar but different. And then we still have a list of payments in our account. How could we navigate that? Well, the first thing I need to do is distinguish between a sealed trait, which is just a coproduct type natively in Scala, and my disjunct type. And this is something I can actually only do with a macro. I can only convert between the two with a macro. It's beyond my capabilities in the type system. So we've got this call to from, which will convert a payment to the disjunct corresponding to the possible types in that payment. So it's disjunct of refund with card payment. So that's the first step. We've got that tool available to us. And by the way, part 1 and part 2 were describing things which exist and work. Part 3, I'm just making this up as I go along. I hope I can get it working one day. But for now, this is speculation as to whether it will work. And this is kind of something I want feedback on. Do you have use cases that this works for, that it doesn't work for? We're going to construct a new optic, and I haven't worked out what the parameter types would be for this optic, but this is going to be a splitting optic, which splits on a coproduct, a disjunct specifically. So let's say the macro produces the disjunct for us, and then we're going to say on a refund, in the case where it's a refund, we're going to access the processed field. In the case where it's a card payment, we're going to access the confirmed field. They're both Booleans, so they are unified. And we could potentially apply it like this. Going from our registration, getting the account, getting the payments, operating on each payment, and then to get past that sealed trait. Remember, the sealed trait itself had no methods. We can't call anything on the sealed trait. We apply the splitter optic to focus our lens on the appropriate Boolean value, which is either processed or confirmed. This will get the values. It's a list of Booleans. And we could set processed true for all of the refunds. We could set confirmed true for all of the card payments if that was what we wanted to do, and get back a registration. That is my attempt to combine these two different ideas into an interesting way, that largely orthogonal. It is an example of, if you were listening to the slides about disjunct and wondering, well, this is nice, but I never have a need for it, here is an example where it can be useful. If you were listening to the slides about lenses and thinking, I don't have a use for this, then keep looking. But just to wrap up, I've shown you two libraries. They're not released yet. The Totalitarian is on GitHub. Optometry, I don't think I've I think that's available on my GitHub account as well. But they're work in progress very much. I'm going to be working on them for probably the rest of the year. It'd be nice to have them done soon. The stuff works, but there's still plenty to be done. The API has to be fleshed out. I'm very, very keen on having feedback on what you think about this, how you think these ideas could come together, how they might apply to your own work. And ideally, I'll have them ready by Christmas. That's my target. It's a month and a day. So that's all. Thank you very much. Thanks. I guess I've got time for questions. Yeah, any questions? Go on.
Have you managed to find any non-hideously ugly way of removing elements from a set with Totalitarian? You have like let's repeat that. So with Totalitarian, you have a set of types basically, and there are some use cases where you might want to iteratively remove types from the set until it's empty. Have you found a non-ugly, hacky, white box macro-based way to do that?
So it's a good question, and it's something that I have looked at. So if you had a list, or sorry, if you had a disjunct of int with string with double, and you wanted to filter out the elements that are doubles, and then have ints and strings remaining. There isn't the machinery in the compiler to do that. So to construct an intersection with an element removed. So I guess you're asking the question because you've tried to do this and haven't found a way to infer a type that doesn't contain this value. I think it's impossible in the compiler. I think it wouldn't be correct to be able to do that, to infer that type, unfortunately, because it would be useful. What you can do is you can always convert values from one type to another. You can remove doubles, or you can convert. For example, you could convert types to options where your ints become sum of int, your strings become sum of string, but your doubles become nuns, and then work on it like that. But it is it does seem kind of lacking that there's no easy way to do this, and the solution is to use a white box macro if you really want to do this. I think you can do plenty of things without it, though. Any other questions? Yeah.
How does Totalitarian compare to shapeless coproducts, or full 7 degrees?
IOTA. I don't know exactly, but the representation is different. So I think IOTA uses it's like a tree of either's, and I think it's a non-linear. As in it's not linear. It branches. So IOTA is quite a cunning implementation in order to get this to work in a nice way. It's probably slower at compile time, and at runtime, I don't know how they would compare. In order to do the runtime tests of the type, you need to do a comparison of type tags, which is slow. I think that's not required in IOTA. Shapeless, I think, uses an H-list, something like that, which involves, I think, quite a lot of recursion to derive implicits to find the value. I think IOTA exists because shapeless is very slow. I'm hoping that my only concern is the runtime performance, because compile time performance is going to be fast. I've tried very large disjuncts of many different types, and it's instantaneous. It has no bearing on the compile time. But I haven't done enough tests at runtime to compare the two different, all the 3 different libraries. But it's interesting. It's something I'd like to look at, and there are potentially ways with macros to improve the runtime performance as well. Rather than using type tags, I could use some other representation. So yeah, ideas to explore there.
Okay. Thank you, John.
Thank you.
While we are setting up the next speaker that we're guesting, you can have a short break of 5 minutes so we can catch up with the schedule. Thank you.
Thanks.